Isn't that an awesome picture? I don't think it's a real picture. I'm pretty sure it's a painting, but at the same time, I'd be pretty scared to be on that bridge or whatever that is with that water coming down on you. Um, but for some reason, with dealing with all these transformations in this chapter, I thought of waves coming over and crashing on top of you because it kind of maybe you could talk about it being a translation, water sliding over, a rotation, water kind of rotating in a circle. If you think of waves, it actually kind of comes over, but lots of transformations. So either way, we're going to talk about congruence transformations today, and it's a thing where we know congruence. We know what congruency is. Two things having the exact same sides and lengths and angle measures. We're going to talk about congruence with using transformations today. So, two things I want to focus on. The goal, I can identify congruence transformations, and I can prove triangles congruent using isometries or these transformations. All right. So let's start off with this. It's a little bit different of a congruence definition than what we're used to. But two figures are congruent if and only if, so there's our biconditional here, um, there is a sequence of one or more rigid motions that maps one figure onto another. So if you can prove that you can either slide, translate, which would be translate, sorry, rotate, reflect um, onto one shape onto another, and it's exactly the same, then they're congruent. And remember, dilations are not rigid motions. Dilations do not keep the same shape. Or sorry, the same size. They just keep the same shape. So be careful with that. If it works that you can dilate one um, and make it so that it's congruent, then it's not necessary, or make it so that it is congruent, then it's not necessarily a congruence transformation. Okay, and that's what we're talking about here. So, looking at this is just our intro example. Which pairs of figures in the grid, if you look at the grid, are congruent? You can kind of tell, I think. But for each pair, what is a sequence of rigid motions that maps one figure to another? So just tell me what you think they would be. So I'm going to start off with PQ is congruent to HG. And I could be wrong, but I'm fairly certain that if you just translate it down 1, 2, 3, 4, 5, 6, 7, 8, 9, and to the right 2, that they would be right on top of each other. So we're just going to say translation will make that work. Okay? All right, let's do another one. I think triangle EDF is going to be congruent to triangle MLN. And the transformation there, I think that would occur. You could do a couple different ones because you could probably reflect over a couple lines and translate. I'm gonna say it's just a 180 degree rotation. And if you look more closely at the points, my guess is they're just opposites. So if we have -1, -1, 1, then we have 1, -1. So they just flip the signs for both of those. Same thing with -5, 1. So I'm guessing we're going to have a 5, or -5, 1. So we're flipping them. Um, 5 and -1. Yep, right there. And then we have -5, 5. So we're going to have 5 and -5, which would be right there. So a 180 degree rotation makes those triangles right on top of each other. All right? Let's find another one. Well, there's only one other set. So we have, let's say, parallelogram or trapezoid A, B, C, and J. I think is going to be congruent to, be careful with the letters, W, X, Y, Z. And my guess is there's a couple different ways you could do it. You could say you're going to translate, then reflect, then translate. I'm going to translate right one and up, what is that, 5, so that they're almost right across from each other, and then you reflect it. So that's what I'm going to say. Translate and reflect. But the point is, you can find these rigid motions that would make one shape go directly on top of another shape, which proves that they're congruent then. And that's what we're talking about in this section. Um, Determining if you can use congruence transformations, if you can make a transformation to show that they're congruent. And then also, we're going to prove some things congruent. So take a look at this one. And here is that definition. Because compositions of rigid motions take figures to congruent figures, they're called congruence transformations. So if it's a congruence transformation, it's a composition of rigid motions or a composition of isometries that takes a figure onto a congruent figure to that. All right? So I would like you to take a look at this one. What is a congruence transformation that maps triangle NAV to triangle BCY? So remember, triangle N and B have to be the ones that are, and then A and C and V and Y. So let's try to think about how we could map NAV onto BCY to prove that they're congruent. I don't know if there's a specific rotation that you could do, and if you could, you have to figure out what point you're rotating around. But even so, it almost looked like V would have to go with C then, but V goes with Y. So here's what I'm thinking. So if you want to pause it and try to look at this for a little bit and think about how you could map triangle NAV to triangle BCY, go ahead and do that for a second. I think that'd be great for you to try to think about it. But now I'm going to talk to you about what I think would work. If I take NAV and translate it over 1, 2, 3, 4, 5 to the left, I'd have V prime. I would have N prime. And I would have A prime. That was my very large prime symbol there. There's my triangle. Now remember, N maps up with B, A maps up with C, and V and Y are supposed to have. So now that they are kind of reflected across each other, that was a translation. I'm going to actually say it's translation -5 and 0. Now we're going to do a reflection over the x-axis. Okay, so if you reflect it over the x-axis, it should map it right on to those points because those are all opposites right there. So if you found that, or if you found a different way, that would be awesome as well. There's usually multiple ways you could do it because you could like reflect it first and then translate it. You could do it opposite. There probably is some sort of a rotation after you reflect that would work, but I'm going to stick with my translation and reflection. I think those are the easiest for that one. So one thing I want to reiterate is the notation. Okay, we just said what our first thing was going to be and what our second thing was going to be. So notation, correct notation for this when you're doing compositions of isometries. Remember, we're translating triangle NAV. Okay, and then we want to put our two transformations and say what we're doing for those. So it's weird because remember the first one you do is actually the second thing. So we use our little of symbol because you're doing a reflection across the x-axis of, axis, of the thing you already did, which was a translation of -5, 0. Okay, so that would be the notation of that. Okay, and that would get you to triangle BCY. Okay, now the second part is proving things congruent, and this is a very loose way of proving congruence because we're really just saying what we would do to prove it congruent. So here's an example I'd like to show you. Remember, if figures are can be a composition of isometries to make them on top of each other, and they are congruent. So what we're going to do here in this example of verifying the side angle side postulate, we want to try to prove that triangle, in this case, triangle JOS is congruent to triangle PAF by, based on given that we're given that angle J is congruent to angle P, side PA is congruent to side JO, and side P is congruent to side SJ. But really what we're doing here is just trying to figure out how we could transform using rigid motions, um, one on top of the other. So the first thing that we could do is slide them. So if we slide this so that A and O, because those two are supposed to coincide with each other, are touching, then we have a picture that kind of looks like this. Nothing else moved, we just slid it. Okay, now if we look at this, we could rotate. If we rotate it until now that the J and the P match up, the J and the P are supposed to match up, or the sides JO and AP coincide, because that's another thing that we were given, theirs are exactly the same length. Let's do that rotation. So we rotate it and we end up getting a shape that looks like this. Now the last thing hopefully you can figure out, and it actually kind of shows it there, is to reflect it. If you reflect it over the line JA or OP, or sorry, JO or PA, if we reflect it, since we know that the angle measures S and F, or sorry, J and P, so that one would be that, they do match up. We have enough now to prove that they are congruent. We know that the points coincide. We know that angle J and angle P are congruent, and the FP and SJ are congruent. So now we have, based on given the side angle side, we use congruence transformations to prove that that is a valid postulate just by congruence transformation. So again, it's very loose. It's just how you could transform one thing onto another. But it's another way to prove congruence, especially when we're dealing with coordinate planes. But right now we're just dealing with general. So what I'd like you to try then is example 4, verify the side postulate. If we know that side TD is congruent to side EN, side YT is congruent to side SE, and side YD is congruent to side SN, we want to prove that the triangles are congruent, and we're going to use compositions of isometry. So if you'd like to pause it and try it, my guess is your way of doing it is going to be a little bit different than my way, but as long as it works, it works. So that's what I would like you to do. Pause it and try this on your own, and I will prove it, and then we can check and you can see how similar or how different yours is from mine. Alright, so here's the steps that I did. I was able to do it in 2 steps. You can see I translated it, and I did copy them pretty much similar. You can see I translated it here so that angle D and angle N are corresponding, they're coinciding. And then rotating it about, I don't know, 90 degrees, 180 degrees, I don't know. It's not a perfect rotation. It depends on if you rotate counterclockwise or clockwise. But when you rotate it around until the corresponding sides that we said we were given are congruent, are on top of each other, it looks like this, and you can see they do match up and they all coincide. And since it mapped triangle YDT onto triangle SNE, we know that those two are congruent. And that's how you do it with, that's how you prove things congruent based off of compositions of isometries. All right, example 5. Just a couple examples of example 5. Are the figures shown at the right congruent? Explain. Well, hopefully you can tell visually they're not. They're not the same size. And you cannot, you could dilate it so that they are, but dilation is not a rigid motion. So they are not congruent. So I'll write that in there. Dilation is not a rigid motion, and you need to only use rigid motions when proving things, shapes congruent using compositions of isometries. All right. Here's a tricky one. It looks like, so identify the errors in planning or solving the problem. Take a look at this. It says the second figure is an isometry image of the figure on the left. Are the orientations of the pre-image and image the same or opposite? See if we can look at it. All right, they look opposite to me. What type of isometry maps the pre-image to the image? Well, it actually take two of them. You could not just take a rotation. If you look at it, you have to translate it and then reflect it. So a rotation would not quite work unless you have some sort of um, reflection or something first. Okay, because this hand has to map up with this hand, and if you rotate it, it wouldn't do so. Okay, so that was the error in that case. And then there's three closing questions. You can answer these on your own. I'm not going to go through these. But what do you know about the corresponding sides and angles of figures that are mapped using a composition of rigid motions? Number two, how can you show that two figures are congruent using rigid motions? And then number three, suppose two figures are congruent. What do you know about the figures, about how the figures are related in the coordinate plane? Okay, that kind of goes back to our two goals. So take a look at those. See if you feel like you've gotten those or not. I can identify congruence transformations, and I can prove triangles congruent using those isometries or those transformations. All right, that's our section on congruence transformations, though. Hope you got something good out of that, and we'll talk to you next time.